Alright, so in this video I want to give a quick overview of what VLANs are and why they are relevant to BMET. Specifically how they relate to the SpaceLabs equipment, which require VLANs in order to operate. This is not by any means a comprehensive overview, but it'll just give a general idea of what VLANs are, why they are used, and how they relate to the BMET classes. So to understand VLANs in a easy to understand way, probably the best way is to go back to why they came about and why they exist. So, for example, you have your home network. You probably have your phone, your laptop, you might have a computer. The computer might connect directly to in this case, the Wi-Fi router, which would be one of these. And you might have one of these that you bought. You might have one that's been sent to you from your internet provider. But this is the general device that connects your devices that are on your local network or local area network to the internet. So information that you want to send to the internet has to go through this device first. And this generally works pretty well. When you start getting more devices though and adding more and more things, especially if you get into a business and you start adding a lot of things, this may not be a great way to go about this. Instead, what you want to do is define it a little bit better, and in this case, to really understand how that works, I'll have to change the example up. I'm going to be splitting this device up. This is actually a combination of several devices, and I'm going to be splitting those devices up into a more pictorial form that's easier to interpret. All right, so for your general network, you would have a router, and this would be connected to another network or the internet, and you would have also a couple different devices. This would be something like a small business. So you have several PCs, maybe you have a server, you have a couple IP phones. You want all these to be able to connect to the internet and to each other, really. The issue is that routers by themselves generally only have a couple of ports. From a theoretical standpoint, it could be two, it could be more. It depends on the type of router, but for this example, let's just say it has 2 ports. Now you have all these computers. Let's just, for this demonstration, let's forget about Wi-Fi. Let's just use Ethernet. So all these need to be able to connect to that port to get onto the internet. The problem is you can't just take this and splice it out between all of these devices. It's not going to work. Unfortunately, it's going to not be reliable if it works at all. It's not really designed to be doing that in the first place. It just generally creates more problems than it solves. Instead, what you need is some kind of middleman, and this is what you would have a switch for. And then each of these devices would have their own connection to the switch. And then you'd have another connection that connects to the router. So traffic you send now, for example, if I want to send a packet from this PC to the server, it would go up into the switch. It would read the hardware addresses of what it is and where it's trying to go, and it would send it to that port that's connected to the server. Send it to the server. Same is true in reverse. It'll go back up through here. One issue is that all of these devices are on the same network. Oops. Let's just call it LAN 1. Now that might be fine for home use. It might be fine for a small business. An issue can come up when you want to try and contain certain types of data. You might want to try and restrict access. Like if I don't want this server to be accessed by everything, then it runs into some problems. There's a couple ways you can try and restrict it. You can set up, this is the purpose of firewalls and access control lists, or ACLs. You could set up a firewall on the server that only accepts data from certain places. You could set one up on the switch itself, called an ACL, access control list, and that can control data that passes through the switch. Unfortunately, a problem with this, it's kind of hard to manage, especially if this keeps growing. For example, let's say these 10 PCs, we add more. Let's say that these are actually now 100 PCs. Let's say we add more servers, and these are now, 10 servers. And let's say we have 100 IP phones. That's a lot of stuff to all be on the same network. Not only because a lot of these devices are going to be using a ton of traffic, especially like IP phones and servers, for example. These all might be using tons of data that these machines down here may never even care about. They may never see it, but they're still sharing the same network. They're still sharing the same switch. We can create problems when you get to the overhead of managing all this stuff. It can start slowing things down. And again, you still have the same problem of trying to control what goes where. The solution to this, from a network engineering standpoint, is to put these on their own separate networks. So now we have LAN 1, we have LAN 2, and now we have LAN 3. And each of these local area networks are now considered to be different networks, which means that their IP address spaces are different. Before, all these were sharing the same IP address domain, which means that they could all connect to each other. We'd all have similar IP addresses to each other. In this circumstance, they can all have different IP addresses. And that becomes sort of an issue when you come to the switch, because the switch is not going to know what to do with that. When it receives a packet from this VLAN, for example, it's going to have a certain IP address. It's going to go up to the switch, and the switch is not going to recognize what device it's trying to go to. And that's when it would be sent up to the router. This is like if you're trying to go to Google or SPC's website or whatever you want to go to. Your computer is initially going to try and ask the switch, where is SPC? The switch isn't going to know where it is, so it sends it up to the router, and the router figures out where SPC is, or the network for SPC. That's the same thing that's going to happen here. If this PC now wants to talk to the server, the switch isn't going to know where the server is in relation to its IP address space. It would have to go up to the router, which then would decide where the address space is. So instead of this path, it would now need to go like this, and then back down from the switch into the server. The issue is that the router and the Ethernet adapter on that router is only going to recognize one IP address space. It's not going to see these other three. It's only going to see one. So when it receives this packet, it's not going to know where to send it, and it's just going to vanish. So you're never going to be able to connect this PC to this server in this situation, unless you can figure out what server or what IP address space this server belongs to, change your IP address on your computer manually to match that, and just bypass the router entirely and send it to the server directly through the switch. That kind of defeats the purpose of having these three networks, though, because the advantage of having three separate networks is you're now able to install a firewall which is able to manage the data or restrict the data and where it's able to go. And that's usually installed somewhere around here. It's either a part of the router or it's a device close to the router. But in this circumstance, that is defeated by having all these devices connected to the same switch. So to get around that, and because switches really need to have their own network, the switches can only be used within their own network. You can have the same setup. So I'll have my router, have my PCs, just put S for server, P for phone. Just pretend they're one server and one phone. It can be 10, it can be 100, doesn't really matter for this demonstration. Now, same thing as before, these are now on their own networks. So we want to be able to control where that traffic is going to and coming from. So in this case, instead of connecting them all to the same switch and just messing things up, we would need to have three different switches. And the PCs would connect to one switch. The server will connect to one switch, and the phone will connect to its own switch. And in terms of the networking in this aspect, these switches are now part of their corresponding networks. So you can see that these match now. And then at this point, you would have your connection going to the router from each one of these. So if traffic wanted to go from this PC to the server now, what would happen is you would send your packet up to the switch. The switch would realize that the server is not part of its network, so it sends it over to the port where the router is connected, goes up to the router. The router figures out where it's trying to go, what network it's trying to go to, sends it out the other port for the switch, or for the router, or sorry, the server, sends it out the port for the server that it's connected to, and then from this switch, it sends it to the server. So you can see the path that the data would take in this circumstance. The same is true if you want to connect to the phone or any other combination you can think of. It's going to have to go through the router at some point. There are some problems with doing this, though. One is you now have 3 different networks, which means you need to have 3 different switches, which means that you're going to have at least 3 ports on your router to route between these 3. And that's a problem just because these are expensive. You know, you're having 3 switches, and routers generally don't have that many ports. Routers may only have 2 ports, 3 ports. It depends on the router, how it's designed, what it's meant to do. But you could have tons of VLANs. I mean, or you could have tons of LANs. This is LAN 1, LAN 2, LAN 3. So you have more LANs. Let's just keep adding on LANs. 5 LANs now. Now you need to have 5 switches. You need to have 5 ports on your router to route between all 5 of these. You might have 10 VLANs. You might have 100 VLANs. It could just keep growing. At some point, you're going to have tons of switches, and you're going to need a router that has all the interfaces under the sun in order to connect to these switches. That's just not feasible. It's not cost effective, and it's pretty inefficient. So that is where you would have VLANs come in. Now, same as before, I'm going to have switch. I'm going to make it pretty big, though. Have our router. And our PCs, our server, and our phone. Same as before, need to be on their own networks. But now we're sort of at the beginning of where we begin with all this, because we have one switch. We're trying to add all these together. We know that's not going to work. So instead, what we would do is we would take a switch called a managed switch or a smart switch, and we would create VLANs on the switch. And the purpose of a VLAN is to segment the switch, or divide the switch up into multiple virtual switches. So instead of having 3 separate switches, now we're going to say, I want these 3 ports to act like one switch. I want this port to act like its own switch. I want this port to act like its own switch. And at that point now, you would have connections going up like that, connection like that, and a connection like that. And that is completely valid. That would work entirely. Now you have 3 separate switches, 3 virtual switches. You have 1 physical switch that's acting like 3 different switches. And it's segmenting these 3 together. The issue is that if these want to talk to each other, they still need a router. They need to be able to, they can't just pass data from one to the other. They need to, like if you have the 3 separate switches, they need to be able to send it to the router in order to connect to it. One way to do it is to just define more ports in this. So I have more ports attached to each one of these, and then I connect those ports up to the router. And that's the same setup as before, where we had the 3 switches, each with their own connection to the router, except at this time, we're just doing it with a single switch. But this is not really that much better, because now we still have to have 3 ports to the switch. We've solved the problem of having multiple switches, but now we have the problem where we still need lots of ports on the router. And like I said, most routers don't have that many ports. So instead of doing that, we would have another port tag, or another port defined over here as a tagged port or a trunked port. Either one, they're the same thing. And we would have that tagged port be a member of each of these VLANs inside of the switch. Now that might seem a little complicated and a little tricky, but the reason for this is these virtual switches still need to have the router to talk to know where this stuff goes. And rather than having 3 separate connections, what if we just multiplexed our data in a way that we can just send it all through a single cable? And it does that through the tagging process. And tagging, what it does is it takes its packet that's coming through it and inserts a tag into it that's associated with the VLAN that this traffic comes from. So going back to our example of routing, in this case, we have our tagged port would be the port that connects to the router, and this would be connected to the internet or whatever. We can go back to our example of following the traffic. So let's say I have this PC that wants to talk to this phone, for example, for some reason. Let's just say it does. So it sends its packet up to the switch with the destination of the phone. This virtual switch realizes the phone's not part of it, not part of this VLAN. Even though it's going to the same switch that's connected to the phone, it's still not a part of that network. So it says, okay, it needs to go to the router. So it sends it up into the tagged port over here. The tag port then inserts the tag associated with that VLAN and sends it up to the router. And then the router does a process called inter-VLAN routing through virtual interfaces. And that's a mouthful. That's a lot of stuff, and it's pretty far out there. Don't worry about it too much. The general idea is that it's able to figure out which VLANs correspond to what network and route between them. So it gets that packet, it reads its VLAN, it reads the information inside of it, where it's trying to go. It then realizes that, it's trying to go out to the same switch, just on a different VLAN. So it just changes the VLAN tag and sends it back to the switch. The switch then associates that packet with the second VLAN, and it sends that packet, like in this case, it would be, like I said, to the phone. It could be to the server, it could be whatever, but in this case, we want to go from PC to the tag port, up to the router, back down to the switch in the tag port, to the port that's associated with that tag into the phone. That seems like a lot, and it kind of is, and it is pretty complicated. But the main takeaway from this is that we're reducing the amount of hardware required and optimizing what we have. By adding just a little bit of overhead, we're able to use a single switch with a single router port. How this relates to the BMET stuff. This thing's really dirty. So we have our server rack, and here we have going from the bottom up, the UPS, which is not connected to anything in this example, so we don't need to worry about it. No, next up from that is the telemetry unit, and then we have the central station. And on the very top, we have our switch. And it has a bunch of ports, but I'm not going to draw them all out. I'll just draw a couple. Now, we also have our ECG and our PC, which in this case is running something like Wireshark because we want to watch the data or whatever we're doing with it. But the main reason we have VLANs in this setup is, for one, the telemetry unit and the ECGs from the central station's point of view need to be on separate VLANs. So up in here on the switch, we say, okay, we want these to be one VLAN, this to be another VLAN. Now you have the ECG connected and the central station connected to one VLAN. So these are essentially connected directly to each other through the switch. Now we have the telemetry unit come up with its internet port or Ethernet port into the switch, and then the second port from the central station goes up to that VLAN. And that's how it has to be set up to work. I'm not sure exactly why that is. That's just how the documentation defines it. the PC in this example would be connected to another port switch, or a switch port, which is a mirrored port, but that's a different video altogether. But to set up the VLANs and the switch, if you've had networking classes, you probably had Cisco. They did it all from probably the command line. This switch in particular uses a web interface, so you need to go on your PC and go to that web interface and configure it that way. But I hope this gives an example or an idea of what VLANs are, why they are used, and how they're used in BMET. You can see here that we have the two switches, the two virtual switches, on two different networks. So if these wanted to talk to each other, we need to have something up here like a router connect these two together. Or the central station would need to bridge the connections or route the connections because the switch isn't able to do that. But we don't currently have that set up. So right now, these are just two isolated networks that aren't talking to each other. And that's sort of how it's supposed to be in the documentation for the telemetry unit. But I'll probably do another video on how to set up the switch in particular, but hopefully that gives a better example of what these are used for. If you don't 100% get it, don't worry about it. It's pretty, it's rather advanced networking stuff. But in order to set these machines up, you need to use VLANs, and this will show you at least what VLANs are.